Is the screen visible?
Yes, sir.
Yes, sir.
Yeah. So this is what the material we prepared for unit 4 and 5. So we would like to publish this as a book. Huh? So anyway, I'll just share this you maybe after 1 or 2 sessions. So yesterday we started about understanding how LPC2148 microcontroller can be understood by understanding the different blocks what is present inside. So I was telling you that there are different blocks is present in this chip called LPC2148, which is a 64-pin quad package. The different blocks are present inside. So we started with the first block yesterday. Today we will study about other blocks, what is available there. Now, so if you look at the different blocks, the first important blocks which comes to our mind is always the block which contains what is called as the core. The core is the block. So this is the one which is very important block. So this core is supplied by the ARM. The core which is used in the LPC2148 is the ARM 7TDMI. Yes, is the core used. As I said, whenever you want the core to work, you have to supply what is called as clock to this chip. So external crystal, which is available in the market, can be purchased and connected to. So connected to this 2 pins. Generally, most of the projects, they use 12 megahertz crystal will be connected here. So once you connect the crystal, it drives the power, it drives the clock supply to this core, and core starting work at 12 megahertz. There is a technology called phase lock loop, which has been used in most of the microcontroller to enhance the clock frequency. So if you pass the clock through PLL, phase lock loop hardware, and enable this hardware and configure it properly, so it enhances 12 megahertz into some factor which you can program it. So by that factor, the frequency of operation becomes 60 megahertz. So using the PLL enabled and using a 12 megahertz crystal, you can make it work at 60 megahertz speed. So this core now is a one block now which drives all of the blocks in the system. Today we will understand about, after understanding the clock, we will understand about the other blocks available. The second block which is present in any microcontroller, which makes it more powerful, which makes it different from the microprocessor, is what is called as the memory, is what is called as a memory block. Now we can see that there are two types of memory available in the microcontrollers. One is the ROM, program memory, read-only memory. Generally, it is implemented in the current state-of-the-art microcontrollers using what is called as a flash memory. You have a flash memory. This is called read-only memory. And you have a RAM, which is implemented using the technology SRAM, static RAM. So these are the two kinds of memory present in almost all the microcontrollers. The flash is the memory where your program is stored. I said this chip 2148, instead of calling 2148, we call it about 214X, because the same family have 2-3 versions of the microcontroller, 2140, 44, like that, 4648. Some different versions are there in the same family. What is the difference? Difference in the memory. You can see that 32 kilobyte. So you can see here 32 kilobyte slash 64 kilobyte slash 120 kilobyte slash 256 kilobyte slash 512 kilobyte. In the sense, what is the difference between the different microcontrollers present in the same family? One of the major differences is what? The memory is what is the difference. So look at here, the memory is different. So whenever you purchase for the project, so microcontroller in that particular family, look at what is the program size you require. If you can able to implement the project with a 32 kilobyte, go for the 214X in that family, go for a microcontroller which has got 32 kilobyte. I require more memory because tomorrow for the future, I require to modify my project. I require a better, I should go for the higher memory, means go for a microcontroller in that family which has got a lot of memory. So 2148 is the highest capable microcontroller in 214X family. So we have taken that chip which is more capable. So how much is the memory present? 512 kilobytes is the flash memory or the read-only memory present in LPC2148. Who provided this one? Who has taken a decision to provide this much of memory? It is NXP Semiconductors. It is not related to the ARM. ARM has supplied only the core. The decision of how much of memory to be presented is the cost decision. How much I have to sell the microcontroller. Based on the costing and the size, they would have decided this option. Next. So now we know that 512 kilobyte of flash memory or program memory is available. Now RAM. RAM is a place we know that where we store your variables. So this is the place where you can implement your stack, and all other things is a SRAM. So how much of memory is present SRAM? In 2148, you have highest memory, that is 32 kilobyte. So if somebody asks, so what is the memory capability or memory capacity of 2148? You should tell 512 kilobytes of flash memory, 32 kilobytes of SRAM is present in LPC2148. Now, how do these memory is connected to here? See, this is the ARM core. Memory is present outside the core. Now this ARM microcontroller has to talk to this memory. Yes or no? But so how do they get connected? They connected through a set of buses. Now we will study about what are the types of buses present inside the microcontroller. How do they connect it? Now, so now we will understand about the three buses what is present here. So there are totally three types of buses are there. Buses means what? Set of pins, set of signals or set of pins, a set of lines which are used to carry the information from the core to the other parts of the microcontroller. See, look at this. This is the one bus. So we call as a local bus. So here you can see that one more bus is there. One more bus. This is called as AHB bus, advanced high performance bus. You can see here one more bus is there. This is called VPB bus. So or VLSI peripheral bus. So there are three types of buses are present inside the microcontroller, inside this microcontroller. All these buses together put together, they call by a name called as AMBA architecture. So what is that architecture? We'll go back and study and come back here. So as I said, there are three buses are available. Inside your microcontroller. So all these three buses, whatever is shown, they'll be called by an architecture called AMBA architecture. What is the meaning of AMBA architecture? It's advanced microcontroller bus architecture. Who defined this architecture? Generally, whenever you use ARM microcontrollers, ARM-based microcontrollers, they follow this architecture. NXP Semiconductors, they follow this architecture in their microcontrollers. So now, what does the AMBA architecture defines? It defines three types of bus. One is called as a local bus. So other is called as AHB bus. It's called as advanced high performance bus. Other is called as VLSI peripheral bus, called as a VPB bus. Now we'll go back to the diagram and analyze that. Now, so the first bus which forms the AMBA architecture is called as a local bus, which is the local bus which is used to connect the memory. So what is the purpose of a local bus? Local bus is used to interface the memory. You know that memory is nothing but so many set of locations is there. When the microcontroller generates one address to fetch the data from the memory, either from a flash or the SRAM, there should be specific instruction to select one among the so many locations. For example, 256, 500 kilobytes of memory locations are there. You cannot read all on one at a time. You can read only from one memory location. Which memory location I should read among the 512 kilobytes of memory locations? That is where the controllers comes into picture. So these controllers will select this address, find out what is an address is available. Based on that address, it enables one memory location for the reading purpose. Then the data will be flown into the core. Similarly, to enable the selected memory location in the RAM, so this internal SRAM controller is there, so which takes the address from the core, decides to look at the address and enables a particular location and gives the data and enables that memory location either for reading or writing. So this SRAM controller will generate the proper read and write signals to this memory to enable it either for reading purpose or writing purpose. So summarizing, the local bus, which is part of an AMBA bus architecture, connects the ARM core to both the SRAM and also the flash memory through the what is called as memory controllers. So since you can see that the bus, there is a 32, what is the size of the ARM core? Size of the ARM core it's a 32-bit microcontroller. What is the size of address bus and data bus? It's a 32-bit. That means that complete 32-bit bus is connected here. And since the memory is also very fast, now controller is also fast. So at the very high speed, that means that at the speed of the CPU clock. What is the speed of a CPU clock? 60 megahertz. We have seen that when the APL is 0 enabled. That means that at 60 megahertz, it communicates with the memory and fetches the data from the memory. So that is why we say that local bus is a high speed bus. Because why? At the maximum speed possible, it communicates to the memory and fetches the data from the memory into the core, or writes the data from the core to the memory. So this is about the first bus called as a local bus. It's called as a ARM local bus. What is the characteristic of a local bus? It is 32-bit in size and it works at the highest speed. What is the speed at which work? At the speed of C clock. We know that whatever the clock you supply to the core, it is called by the name as CCLK. CCA means CPU clock. So CPU clock, whenever I use in the explanation further, that means that what? The speed at which your core works. So the CPU clock by default, if I don't specify anything, I'm assuming it's a 60 megahertz because PL0 is enabled. Now we will go to the second bus. I'm audible?
Yes, sir.
Yeah. Now I'll go to the second bus. What is the purpose of a second bus? So the second bus, it is called as a high performance bus. It's called high performance bus. But the speed of the high performance bus is less compared to the local bus. Whenever you reduce from one speed to the another speed, a circuit called as bridges are used. You would have heard in the networking. What is the meaning of a bridge? A bridge is a one which converts one speed information to another speed. That is communication between the core and the bus, whatever you are generating. That is what is called a high performance bus. The speed mismatch is there. The bridge is a one which reduces speed of from the local bus to another bus called as high performance bus. So that bridge which transfers the information from local bus to the AHB bus is called as the AHB bridge. So AHB bridge transfer the speed from local bus speed to the AHB bus speed. Now what is the use of AHB bus? AHB bus is used to interface to very important block called as vectored interrupt controller. Vectored interrupt controller. So apart from that, it is also used to connect to the 8 kilobyte of USB. Since we are not studying about the USB as a part of the study, so as a syllabus, so I'm not focusing on anything about the USB. So one of the important thing we'll connect is what? The ARM 722MI AMBA architecture provides a second bus. The name of the second bus is called AHB bus, Advanced High Performance Bus. The speed of that bus is less compared to the local bus. So this bus is used to interface one of the important block called vectored interrupt controller. What is the meaning of an interrupt controller? I said when I was discussing about the unit 2 architecture, this core receives the request, what is called as interrupt request, in the form of FIQ and also in the form of IRQ request. Who generates the request? The different peripherals are present inside. Look at this. All these peripherals, whenever they require a service of a core, they request the core through an interrupts. What type of interrupts? Two interrupts are there. One is FIQ, other is what is called IRQ. When this chip has got only two pins are there. One is an FIQ, one is one IRQ. But how many devices are there? There are number of devices. If you go down, there are number of peripherals are there. Each peripheral generate one or two interrupts. So, but the core has got only two pins are there. But the people who generate the request is what? More are there. So somebody should catch these many requests and select one among them based on the priority, based on the masking, based on the selection, and generate either IRQ or the FIQ to the core. So that logic in microcontrollers or microprocessor, which performs this job of what? Receiving the interrupt request from multiple devices and selecting one or two among them based on the priority, masking, the preferences, and giving that selected one to the core is called as a vectored interrupt controller. As the name says, what is that? Vectored interrupt controller. Every interrupt, whatever you generate, will have certain address associated with it. We will study about the vectored interrupt controller later. So a vector interrupt controller responsibility is what? Selecting the request from many of the devices, that is peripherals, which are all these blocks. Select one FIQ and one IRQ from that. Yes or no? And whichever one is available there, that you generate to the core. We know that core has got two pins. One is called IRQ, other is called FIQ. So that job is called as vectored interrupt controller. So before you use a vector interrupt controller, the core has to program the interrupt controller how you have to behave. What do you mean by behaving? Which you have to give importance. For example, you get an interrupt request from two devices. You get from ADC also, you get from UART also, which has to be given a more priority. You should be able to inform that vector interrupt call how you have to behave. So that behaviors are being programmed by the core. That is nothing but the programmer in the beginning of his program. So these are all done by the vector interrupt controller. Now we have finished the two buses. What are the first bus? A local bus, which is used to interface the flash memory and the RAM through the memory controllers. The second is called as a local, there's a high performance A per bus is called HB bus, which is being generated from HB bridge from the local bus, which is used to interface a vector interrupt controller, which is used to select one or two interrupt requests from the many multiple interrupt requests. So now we have finished the second bus. Now we will go to the third bus. Third bus of AMBA architecture is called as VPB bus. It's called as a VLSI peripheral bus. You can look at this. This is called VLSI peripheral bus. So this bus, VLSI peripheral bus, so this VLSI peripheral bus is the one bus. Look at this bus. This is the bus which is available, which connects all these peripherals. Look at this. This is the one which connects all the devices, whatever the peripheral supporting devices you have it. If you want to store the date and time, use a RTC. You want to communicate to the computer, use a UART. You want to talk to the SD card, use an SPI. You want to talk to the sensor, use an I2C. You want to connect a USB device. That means that this device is to be connected to computer, use USB. That means that you want to read ADC, you read here. You want to generate some unlock signal, use sound signal. You want to generate, use a DTI converter. You want to control the motor, use a PWM. So like this, so many blocks are there. All these blocks are intelligent blocks. In the sense, when I say intelligent, what does it mean? That the functionality of each of these blocks can be programmed. The way it has to behave. For example, you take an UART. I can program this UART to communicate to a computer at 9600 baud rate, or I can communicate it 18200 baud rate. That is, I can decide. That means that a programmer can program into this chip how you have to behave. That means that every module in this controller can be programmed. So who has to program this one? Nothing but the programmer comes into picture. How does a programmer will do it? A programmer is always what? One, he writes his instructions using an assembly or C language into this core. I said, now you know that. That is you write your program and getting executed by the core. Core in turns talk to these peripheral blocks using a bus. So what is the bus I am using to talk to any of the peripheral blocks? The bus is called VPB bus. It's called VLSI peripheral, the bus. This bus operates at low speed compared to the local bus and HB bus. Since the speed at which this bus works is less, because why? Because these are all the peripherals. Peripherals do not work at that speed at which the core has to work. See, the purpose of core is what? To execute the instructions at highest speed possible. But whereas all the devices outside the microcontroller, they work at a very less speed. For example, you talking to the computer, what speed it works? 9600 baud rate. That means that the speed at which the peripherals will work is always less. That is why we use the bus which can work at a lower frequencies. Whenever you work at a lower frequency, the advantage is that you are not going to lose the data, and it is efficiency and the reliability of the system is also more. So we use the lower speed bus called VPB bus to talk to these peripheral blocks. Now, this bus ultimately is generated from which bus? Which is generated from HB bus, and HB bus is converted into VP bus using another hardware circuit called as AHB to VPP bridge. So AHB to VPP bridge. Now, how much it has to convert? For example, I have a 60 megahertz is the speed at which my CPU clock is available. Now, let's say that the CPU clock 60 megahertz, I want to convert into VPP bus, which should be lesser than that 60 megahertz. So generally, by default, I can able to program that divide by 4. Most of the times we use the default value so that 60 megahertz will be automatically divided by 4 and you'll get a 15 megahertz. How much you have to divide the CPU clock into the clock of VPB bus, that can be decided using what is called as a VPB divider. There is a VPB divider register is there. I can put the values into this one. I can decide how much is my VPB clock. So now I'm introducing another clock that is called as peak clock. So one clock I've introduced called CC clock. Now another introduced peak clock. Peak clock is what? Peak clock is the speed at which your VPB bus is going to work. So VPP bus works at a very lesser speed, and the speed at which VPP bus works is called as a peripheral clock. This is the speed at which the peripherals will be communicated to the core. So from where the P clock you get it, there is only one clock for the whole of the system. That is nothing but supplied from the crystal. So that is called C clock. So C clock is responsible for generating what is called P clock. So by default, most of the projects, if C clock is 60 megahertz, P clock is always 15 megahertz. By default, we'll get the divide by 4, but I can change it. So who decides how much is the P clock to be generated from the C clock? That decides the VPP divider. So in the program, you can control this one. So summarizing now. So one of the important blocks what is present in the microcontroller is called as ARM core, which is connected to all the different blocks like a memory, vector interrupt controller, and the different peripheral blocks using the set of 3 buses. Those 3 buses are called as first as a local bus, which operates at CPU clock speed, C clock speed. Then we have an AHB bus, advanced high performance bus. So, and then we have another bus called as VPB bus, very VLSI peripheral bus. So local bus, AHB bus, and VPB bus, together these 3 buses will form a bus architecture of a microcontroller that's popularly called as AMBA bus architecture, advanced microcontroller bus architecture. So the first bus was used to connect the memories, second bus used to control the vector interrupt controller, third bus used to control all the different peripheral blocks. 2 speeds we refer whenever we work in the programs, whenever we develop a programs, do calculations, we always remember 2 speeds we will be referring it. One is a CPU clock speed, other is a peripheral clock speed. Peripheral clock is the speed at which it communicates with all the peripheral blocks, including I2C, USB, everything. CPU clock is the speed at which your instructions are executed in the ARM core. Am I audible? Am I audible?
Yes, sir.
Yeah. So now we have completed. So 2 important blocks of an ARM architecture. One is a core, other is a bus architecture. Now, so once that is finished, now we will go to the other blocks. So we can learn the different blocks what is present here. We can learn all these blocks what is present here by what is called as understanding so the requirement. So generally the microcontrollers, whatever we study or whatever we use our projects, has to satisfy certain requirements. What are the requirements it has to satisfy? What are the requirements a microcontroller has to satisfy? A microcontroller is required to satisfy the following things. Then only I can able to use the microcontroller for my projects. So if you look at this, the microcontroller, whatever we have studied this microcontroller, this chip is used for the developing on hardware boards like an Arduino board or Raspberry Pi board, which is used for building the products. Now, what are the requirements a microcontroller should provide to support building your products apart from the memory? So most of the devices, whatever you take outside the microcontroller, you're putting them and connecting them to the microcontroller. What type of connections you make, that depends upon the peripheral what you use it. For example, if I take one sensor, yes or no? If I take one other component LED, if I take one switch, yes or no? The requirements or the working of all these chips is different. The way LED works is different. The way sensor works is different. The way switch works is different. The way the motor works is different. So variety of systems will be present in your project, and making them all connect to your microcontroller, it is not one set of signals are sufficient. You require a variety of signal to be supported by microcontroller chips. Only when you have that variety, that means that variety of interfaces are possible, and then it's called as a system on chip. When you call a system on chip, it's an SoC chip. When everything it has got inside and it supports all kinds of peripherals outside, then only you can call as a system on chip. If the variety is not there, then what is the loss? You have to put external some circuits to generate that variety. For example, I want to interface this to a, let's say, a sensor, analog sensor, which is, let's say, temperature sensor. That means that if I do not have an ADC, then what will happen? Let's say I do not have an ADC. I want to interface an analog sensor, temperature sensor. I want to interface. Then what do you do it? Since it is not available analog pins, then what should I use? I should use an external ADC chip, and then I have to connect it. It is possible. It is possible to use a microcontroller to connect anything. But if the variety is not provided in the pins, then what will happen? You have to use an external circuits outside. The more the external circuits you use, for example, look at the PWM. If the PWM block is not present, you cannot control many motors simultaneously. Then what you have to do is you have to use some external hardware to connect your motor circuits. So that means that the more, for example, you want to store the date and time because you are using for time tagging of the time. So you want to record the date and time sampling you're doing in a sensor. You're deployed a sensor in an agriculture field. You want to collect certain information based on certain timings. In morning 9 o'clock, in the evening 5 o'clock, you want to record it. Then where do you store your time? Who will update the date and time? Then you require what is called an RTC is available. So then you can connect a sensor there. You can update the date and time stamps. So that means that if these blocks are not present, yes, it is possible to use a microcontroller to interface all these things. But what will happen? The hardware which is not present inside, you have to put it outside. The hardware which is not present here, you have to put it outside. So you don't have PWM inside, you put the PWM outside. So the more complex, more capable microcontrollers are what? Those microcontrollers which have every block present inside. Then what will happen? The investment on the product will be very less because you don't require to put any external hardware. Directly take the peripherals and the sensors, connect to the microcontroller. Your project is over. In a very small board, you can able to finish your project. That is why when you choose a microcontroller, always you have to ask these questions. Does this has got a GPIO? Does it has a PWM? Does it has got a DAC? Does it got a ATC? Does it got a capture? Compare registers are there? Does it got a timer? I2C, all those things. So today, now another 10-15 minutes, we'll study about what are the blocks generally a typical microcontroller should provide inside, should has got inside to make it a versatile microcontroller. So we will start one by one now. Now, the block which is present inside, which is generally used to interface LEDs, switches, LCDs, and all those type of block is called as GPIO block. So what is the first block we are going to study now? General purpose IO. What is the general purpose IO? General purpose IO is like a digital input out pins. What does the Arduino has provided? You know that Arduino has got how many pins? 14 digital pins were there. Yes or no? Those through the digital pins, you are connecting to the LEDs, you are connecting to the LCD and everything. So any microcontroller is required to talk to the LEDs, talk to the keys, talk to the LCD. So for that, you require what? Digital input output pins are required. So the block inside a microcontroller which provides that type of pins is called as generally GPIO block, general purpose IO block. Because why? The purpose of the pins, it is decided by what? The programmer. It is not being defined by the microcontroller. Anything in the world you can connect it. If it falls into what category? It falls into digital input output category. Nothing is defined. That is why it's called as a general purpose IO. It's like a general purpose computer. So when you purchase a computer, the task is not defined. For whatever purpose you can use it. Similarly, these pins, the task is not defined. In all other cases, task is almost little defined, but here task is not at all defined. It's you take a decision for what purpose I'm using input output. So, but only thing you make it mind that these pins are called digital pins. That means that, so this chip, so unlike the chip what we studied in Arduino, so and Atmel, this chip, it works at 3.3 volts. So what are the pins for that? We'll finish that anyway. I'll just deviate it from there. I'll come back to that piece. So look at the pins. What does the chip provides? So this chip provides pins for power supply. So it's not indicated here. Okay, so this provides a pins for the microcontroller interface. Okay, I do not have the, okay, here. Okay, so look at here, look at the chip here. I just, you're able to see this? Yeah, okay. Look at that. These are the two pins which are used to this microcontroller, the power supply. So we have studied that there are two pins available till now. Among the 64 pins, what are the pins we studied? Two pins. One is for what? Crystal 1 and the crystal 2 is the two pins we have studied. So apart from the crystal 1 and the crystal 2, the two pins, whatever you studied now. So I'm introducing another two pins. What are the two pins? One is a VDD, other is a VSS. So VDD for this chip is 3.3 voltage. That means that if you want to work with this chip, So how much is the power supply you have to give it? 3.3 volts. And this pin VSS is what? Substrate. It's called for CMOS technology. It's called a substrate. You have to ground this pin. So these are the two pins which is available. Many times what will happen, they provide an extra VDD supply. For example, see 43 is a VDD. You can look at here. 23 is also VDD. 25 is also VSS. That means the same thing is there. So here also one VSS. Why do they provide more number of power supply pins? Because the circuits whatever present inside. Yes or no? The blocks which are near to that they can take from here. The blocks which are here they can take that. So proper power distribution happens here. Yes or no? It's not overloading of a particular pin numbers. So particular lines. So they can distribute properly. So see here also one substrate is there. One VSS ground is there. So now we have seen that there are few pins are available on this chip. So which provides a power supply to the ground. So multiple pins are provided for the proper power distribution. So what are the names of the power supply pins? VDD and the VSS. VDD is for the drain voltage, that is you have to give 3.3 volts. VSS you have to give that is a ground pin you have to give it. Now going back. So now we were discussing about the GPIO block. So GPIO block, I said that it is used to connect to the general purpose logics like LED switches and the LCDs and everything. Now this block provides a set of two ports they provided. It's called port 0 and the port 1. So port 0 provide each of the port is a 32-bit port. Each port is a 32-bit in size, but in one port we use only 16 pins. In another port we use about except one or two pins, we use all the pins we use it. We will study this in detail a little later after the discussion here. Now we have understood one block, GPIO block. Now we'll go to the second block. Whenever after interfacing the GPIO pins, the other block which is very essential for any microcontroller is to provide a facility to read analog input. So that block is called ADC, A to DC converter, ADC converter or ADC. Two ADC are there here, ADC 0 and ADC 1. Each will provide around 8 inputs are there. We'll study them in detail. So these, through to the ADC converters, I can able to read analog signal here. What is the range of the analog signal? 0 to 3.3 volts is a range of the analog inputs I can able to provide it. This is similar to the 6 ADC point A0 to A5, what you have studied in your Arduino board. So the number of analog inputs in Arduino was very limited. How much? Only 6 you had it. So look at the advantage of LPC2148. Already we have seen a lot of advantage compared to the Arduino. So the memory is what? 512 kilobyte. The memory capacity is RAM is what? 32 kilobyte. That itself is a huge compared to your Arduino. And this now I'm looking at ADC. So how many ADC? How many ADC? 2 ADCs are there? 8 plus 8. So there are so many analog pins are available. How many GPIO pins are there? I say 32-bit plus 16, 48 around. So in the sense, number of digital input output pins, number of analog pins are very high compared to your Arduino. So that you can able to connect hundreds of systems, hundreds of small signals you can able to connect to these microcontrollers if you combine both analog and digital signals. Now, there is no D2A converter available in your Arduino board. Yes or no? You use PWM signal itself to emulate what is called as your analog outputs. Here, an explicit hardware D2A converter is there. You don't require to emulate that. So this D2A converter generates analog output. For example, the MP3 player, if you want to design a project MP3 player, LPC2148 is most suitable. You can connect an SD card, store your songs, provide a panel, you can select the song, you can play them, connect a speaker using an audio amplifier. So amplifier if required, you can use them. Otherwise, you can use the proper transistor, one transistor, and you can connect to your speaker directly. So A out is nothing but the place where you can generate your analog signals, including the sound. So now we have studied general purpose IO block, you studied A to DC, ADC block, and we also studied what's called D2A converter. Now we'll go to another block. One of the very important blocks which any microcontroller generally provides, including your Arduino microcontroller inside it has got, that is called timers. So what is a timers? So timers is an hardware counting device. Generally, whenever we want to count certain things, we want to produce 1 second, 2 seconds in a program. How do we do it? We write instructions in the ARM core, loop it many number of times. The loop produces execution of repeated instruction that generates a delay. But that consumes the power of your microcontroller. That means that you lose the time of a microcontroller. Since the microcontroller has to do so many other jobs, you cannot use the microcontroller for counting jobs. In such cases, whenever you want to generate a delays, you want to count certain events, we people use what is called timers. So timers are nothing but a hardware blocks which are used to generate a different time delays and for counting applications, where you can relegate the jobs of microcontroller to this block. So you can microcontroller can tell this block, you keep counting it, I'll come back to you and take the value of what is a count. That means that, for example, you use a microcontroller as a counting device. You are fitting the microcontroller product on a door, smart door. You want to keep how many people have entered in a day. You don't require the microcontroller to do this job. So you can delegate this work to a counter, a timer. You can tell this block, keep counting it. So after, at the end of the day, I'll come back to you and give me a count. That means that, so microcontroller can delegate the works related to timing and the counting to a timer block. That is why most of the microcontrollers will have the timers, so that time microcontroller can able to focus on other so many other jobs. These are the blocks of a timer and a counter. Now, as I said, any microcontroller system, you are going to receive the data from so many devices outside. You are connecting a printer, so you are connecting a sensors, so you are connecting a keyboard. So many devices you're going to connect it. So whenever microcontroller is doing its job, it's executing its program. If some device you have to connect it to two important devices, maybe the keyboard and a sensor. If the data comes from this device, you have to stop your program and attend this device. Then what should you do? How do the microcontrollers provide a facility to receive the data, to receive an attention from a devices? That is called as interrupts. So interrupts, external interrupts are nothing but the pins provided to the microcontroller. Through the pins, the devices can generate a request to a microcontroller. Whenever microcontroller receives a request on those pins, microcontroller stops executing and branch back to what is called service routine, which is written in the memory to service these devices. If these pins are not available, it is very difficult for the microcontroller to look at these devices. Because why? See, when they assume that there is no interrupts are there, then what is a way to find out if something is happening here or not? Then only method is what? Through the program, you should always keep checking every 1 second. If something is there, like that. Assume that somebody is coming to the house. There is no bell is there, and they cannot knock the door. So how do you attend them? You should keep going to the door, see that if they have come or not. You should keep watching at the door. Assume that they cannot knock the door. There's no way to raise your attention. Yes or no? There is no bell is there. How do you find out somebody is there or not? You should keep go there and watch it. Yes or no? So similarly, if there is no way for the devices to talk to the microcontroller through the interrupts, there is no way you can able to take the data unless you repeatedly attend to these devices in the program. So that again, what drains out the time of the microcontroller. So to make the microcontroller focus on other things, always interrupts are used. So whenever the request comes, then only at that time you bring an attention to these devices, attend the service, that is service these devices, and go back to your program. That is why external interrupts are provided. How many interrupts are provided? ENT0 to ENT3. There are 4 external interrupts have been provided by the LPC2148. So that is also more when compared to your normal microcontroller, what is used in Arduino boards. Now we have studied all the blocks what is present in the left side. So I will summarize those blocks what we studied. So the different peripheral support blocks provided in the microcontroller are what? Number one is what? General purpose IO, which is used to interface LCD switches and keyboards. ADC converter, which is used to read the analog data from the sensors. DTA converter, which generates analog signal like a sound signal. Then we have a timers, which can able to reduce the job of a microcontroller and take care of all the counting and timing related jobs. And the interrupts to take the attention of the attention required devices to hear. There's one more block was there that is called PWM, pulse width modulation. This we have seen in Arduino. There are certain pins are called PWM pins are there. Similarly, in case of LPC2148 microcontroller also, it provides PWM 0 to 6. See that there are these many pins are there. There are about 7 pins are here. PWM 0 to 6. So these pins, PWM pins, are used to generate a PWM waveform simultaneously, so that you can able to control the different types of motors, the speeds of the different waveforms of different duty cycle you can able to generate, that you can use to drive the color LEDs and other things you can able to do it. See that these PWM signals are different from the digital signal. So in Arduino, we are used for both together. So now either you can, some pins can be PWM or a digital pins. Here it's not like that. There are so many pins available for digital input output. Apart from that, there are so many pins are provided for the PWM. So if you look at these pins, there is a lot number of pins are available here to interface to the external world compared to the normal 8-bit microcontrollers like what we used in the normal boards like an Arduino boards. Now, so let's come back to the another 10 minutes. I'll continue. Am I audible?
Yes, sir.
Okay. So now I'll continue with the blocks which are present on the right side. These are the blocks which are very popular, which are very specific applications. In the sense, normal microcontrollers like an 8051, which is from Intel, they do not provide these utilities at all. You will not find many of these blocks in a normal microcontrollers, 8-bit microcontrollers. This speaks about the capability of a microcontroller. I say LPC2148 is very flexible, highly rich microcontroller with the interfacing facilities. So why LPC2148 is very powerful microcontroller for embedded application? Because of the support of the blocks what is provided on the right side. Now we'll study one by one what is the purpose of it. So microcontroller LPC2148 can connect to an external world. I said external world is what? External world is nothing but a set of either simple devices like an LED, LCD, switches, sensors like that, or the external world will be complex device also. For example, you want to talk to another microcontroller, you want to talk to another a small intelligent system, you want to talk to other computer, you want to talk to the cloud. That means that the devices which are present outside the microcontroller sometimes are dumb devices like LED, LCD. I call LED keys are dumb devices because they don't have an intelligence. So because you have an analog pins and digital pins, you can connect them. That's all, finish. But there are so many devices which are outside. For example, you want to connect to a printer. So you want to connect to another microcontroller. You want to connect to a computer. You want to connect to IoT devices. They are intelligent. In the sense, whenever you want to connect a microcontroller to an intelligent devices, what comes into picture is called as a protocol comes into picture. That means that you should understand the chip. You should understand how this chip communicates. Yes or no? Then only you can able to connect to the microcontroller. To support variety of such devices, variety of such protocols, most of the microcontroller provide what is called as 3 interfaces provided. 4 interfaces they provide. So these interfaces are called as serial interfaces, which we have studied in ARM also, Raspberry Pi also. What are the 4 popular serial interfaces are provided in any microcontroller? What is the meaning of a serial interface? Serial interface means the data whatever communicated between your external intelligent peripheral and your microcontroller are serial in nature. Serial in the sense the data which goes out of the microcontroller is 1 bit at a time. Even though it's a 32-bit microcontroller, you want to push the data, not all 32 bits comes at a time. You want to push what? 1 bit at a time. If you want to write something 32-bit at a time, only place is what? Code to the memory. That's all. Code to the memory is only 32-bit. Yes or no? Or maybe the code to the peripherals inside is 32-bit. But when you want to write it from inside to the outside to the intelligent devices, your system, you can write only what? 1 bit at a time. That means that to establish a serial communication between the intelligent devices, 4 main protocols or standards existed in the market. So these, all the microcontrollers provide these standards. Some microcontrollers may not provide some of the facilities, but most of the devices, whatever available in the market, any intelligent device you take from a color LCD to any touchpad, any intelligent devices, you just check with the manufacturer what type of interface they should fall into one of the 4 only. So that means that if you know these 4, I'll tell you, you can master embedded system. Any microcontroller you take it, you can able to program them because these are the 4 which are extensively used in all embedded system. We will study one by one now. What is the first one? First one, universal asynchronous receiver transmitter, which is similar to UART of your Arduino board. In Arduino board, you have a TXD, RXD pins are available. So those type of communication is supported by UART. So at the end of the unit 5, we study each of this block in detail and we program in detail also inside. We will study about in detail. So now I'll just explain what is the protocol. So UART provides universal asynchronous receiver transmitter, a serial protocol where you have a TXD, RXD lines are used to connect them. Now, how many UARTs are there? 2 UARTs are there. So that one you can use to connect to a computer, one you can use to talk to an IoT device also, IoT gateway also, you can able to talk to them. Now, so the second block, the second protocol is called I2C protocol. So I2C protocol is another protocol. So through they provide a lines called serial clock. So and the serial data. 2 blocks are there. So SCL0, SCL0, SDA0. Other is block is what? SCL1, SD1. So using these two lines, it can hook to many number of devices. So what is the difference between a UART and I2C? In I2C, you can use the lines TXD, RX2 to connect only one device, whereas I2C protocol is such that the same two lines, that is SCL, clock, and the data, you can use it to hook to many devices. That means that the bus is a multi-device. It supports multiple devices. Same bus, you can hook to many devices. That is the advantage of an I2C bus compared to UART bus. Now, so but I2 UART supports a longer distances, whereas I2C does not support longer distances. For example, if 10 meters are there, yes, you can use an UART. If you want to connect 10 meters, you don't use I2C bus. If you want to connect another IC which is near to this IC, then we use an I2C bus. So it depends upon the requirement. You have to choose which bus is required, which protocol you have to use it. The next third protocol is called SPA protocol, serial peripheral interface. So this provides the 4 signals. So serial clock, master output, serial input, master input, serial output, and serial selection device, that is a slave select device. So there are 2 such blocks are present here. So that is a set 1 and the set 2. So this is used generally for high speed data transfer. When you want to connect an SD card and talk to the SD card, generally we use this protocol, we use SPA. I2C is generally used to connect the sensors and the things. Now, the fourth interface or the serial protocol which supported is called USB. As I said, so USB is of 2 types. USB is a what is called USB device support, USB host support, or what is called OTG, USB host and device, both the supports are there. So this LPC2148 is a lower end in support. So just to provide preliminary support for the USB. It provides only device support, in the sense whenever you design a product using LPC2148, this can only be a device to another computer. For example, what is a USB host? A computer is called as a USB host because you can connect other USB devices like a mouse, keyboard, pen drive to the computer. Similarly, you cannot make this as a computer device. You cannot connect, there is no facility for connecting a pen drive to your LPC2148, not possible. But this LPC2148 can be used to design a mouse. LPC2148 can be used to design a printer. So that means that LPC2148 you can use to design a device so which can act under another host. So that is a limitation of this one. So whenever you want to build a project, your project should be able to provide a pen drive support so that you can read the file system. No, you cannot go for LPC2148. This is where you should be able to think what are the limitations. In such cases, you have to go for the next version, LPC1768, which provide OTG support on the go. In the sense, it can act as a device also. It can also act as a host also. So this provide USB device support. So this is also serial in communication. So these are the 4 serial protocols, embedded protocols supported by your microcontroller called LPC2148. Summarizing, what are the protocols? UART protocol, I2C protocol, SPA protocol, and USB device support. So now we have finished what is called serial interface. Now we'll come back to the last 2 blocks. Another 5 minutes, I'll just take it. So one is called as the real-time clock, or TC. I said, whenever you want to build a project, you want to do a date and time stamping. You want to store the date and time of the samples collected. So in such cases, you require a block called RTC block. As the name says, real-time clock. If you connect a battery, see that there is a signal called battery is there. You can see that VBAT is there. If you connect a battery to this chip, so with the help of battery, those batteries can run for 1 month, 2 months, even if you are able to use rarely, depends upon your program, it can work for 6 months also. Just use normal 10-15 rupees battery. This battery can hold the date and time of your system. Our real-time clock is a block which enables storage of date and time inside your system with the help of. Then we have what is called watchdog timer. So watchdog timer is very essential for debugging purpose. For example, you build a product using LPC2148, and let's say it has got hanged in between. So then what will happen? Many times you don't have the manpower to monitor your things like a computer. It will be deployed at a remote place. The system is hanged. How do you know that? To overcome such type of hanging, we use watchdog timer. Watchdog timer, as the name says, it's like a watchdog. So you set a timer for certain count. So you should, in the program, in between, you should go and reset this count. Always in between, you should be able to reset here. For example, I have set for 1000. In between the program, before 1000 becomes 0, I'll go there and rewrite the 1000 here. So in between the program, I keep going and updating this count, always to making it 1000. So if you don't update this count, what will happen? 1000 becomes 999, 100, 50, like that, it becomes 0, and the immediately whole system will reset. So watchdog timer is a method to reset the system automatically if particular count is reached. So that is why what we do, programmers in between your logics will be keep updating it. That means that what something is going on meaningfully. So whenever something is hang happened, what will happen? Then it will not updation will happen. It becomes zero and reset and start from the beginning. So automatically restart if there is a hanging happened in your program or the system because of the hardware or software reason. For that, watchdog timers are used. So system control to generate different control signals which are required to collaborate or control the different operations within the block. So this completes LPC2148 architecture. Once you know the meaning, it's very easy to write it actually. So summarizing, so you have a core, you have a memory, you have a vector interrupt controller, you have three buses, local bus, AHB bus, and what is called VPB bus. You have two clocks which is used inside. One is CPU clock, other is a peak clock, and we have around 10 different blocks of that, starting from GPIO to connect LCD LEDs keyboards, PWO to generate a PWM to control the motors. You have ADC converter to read the sensors, DTA converter to produce sound like signals. So you have a timers to manage the time and counting things. You have an external interrupts to receive the attention of the devices from outside. You have four serial interfaces starting from the UART protocol, I2C protocol, SPI protocol, and USB 2.0 device support. And also you have support for storing the date and time stamping RTC and watchdog timer to avoid the reset in the hanging of the system. So these are the different blocks and how a typical microcontroller will look like inside the chip. So if you have any doubt, you can raise your doubts. Am I audible?